Like Patrick said, I'm Roberto. I come from Puerto Rico, which is quite a little bit ways, 25 horas de viaje, 25 hours to get here, but I'm very happy, a little bit tired, but I wouldn't miss it for the world. Um, I'm going to be talking about the best way to, the tool set that we use and how it evolved over time to do geospatial. Oh, I'm trying not to speak too much. But if can you hear me now? This level is good. Okay. Um, I'm going to be talking about the stack that we have evolved over time doing geospatial applications. We started with a pure Django system, and over time we have to adapt. And this talk is about having to let go a little bit of what you like in versus what actually works and how you can bootstrap an application much faster. So I've been doing software development for almost 30 years now. I've been working with Django since the days of the beta versions and 15 years with Python. And I come from Puerto Rico, and I work for Critical, which is a software development company that does a lot of software development for the government. So we have to work with very good cache strap environments. I'm known for Mayan EDMS, which is a document management system built on Django. It's used by the state of California, Intel, and Cemex and Deloitte Touch Komatsu, one of the biggest world companies in accounting in the world. I'm also known for Awesome Django. If you ever need to do a Django application, you need an app for something, take a look at Awesome Django. It's a curated list of apps that could help you save the day in a rush. This is one examples of the software we do for the government. This is a toxic emissions map for the Environmental Protection Agency in Puerto Rico and the State Institute of Statistics. And it's a portal that will allow citizens to select a place where they live or they are interested in, and will give you an inventory of all the toxic emissions that are being emitted in your area and whether they are carcinogens or dioxins, and is integrated into Wikipedia. So after doing how I got here, I used to be the director of software development for the government of Puerto Rico, and at that time we had a very big challenge. The governor of Puerto Rico issued a new order forcing all government agencies to start sharing their data with each other and with the public. The problem was that they gave us the order, but no budget, no guidelines. So I had to create an entire platform from the ground up, and we call it Libre, which means free in Spanish, and it stands for the Large Information Batch Restructuring Engine, which will be like an ETL in real time that will convert all the legacy file formats in the government into a modern file formats like JSON, YAML, and GeoJSON, and will allow the community, the people, access to government data. And it allowed, for example, to do joins across different data sets, even though they were residing in different government agencies at different file formats. For example, this is a crime map where the points of the crimes were being extracted from an Excel file, but the geofence is a shapefile being extracted from the planning board. So we were able to do joins in real time from data in different government companies, and the language that was created was a REST language, a REST query language, in which the URL will actually be able to build the map. And if you combine many queries, you can create entire dashboards. And this was a project that was created with the help of some great interns. And we created a dashboard for the governor of Puerto Rico when he can have an eagle-eye view of the situations of different government agencies and infrastructure issues. And it was released as open source in GitHub. It was the first official product of the government of Puerto Rico. And it was used by a lot of government agencies and even governments of other countries. And it was free and it was working great. And then I decided to leave government, and they had to shut it down. It turns out that the project had a hit by boss coefficient of 1, me. So as soon as I left the government, the knowledge to continue the project and keep improving it or even keeping running was lost. So they decided to scrap it down, even though it was working great, because the people had come accustomed to being able to access government data. They reclaimed that they still wanted access. So the government went up with this project, with this product. It's very expensive. It's usually, the cost is what 1 or 2 government employees make in a whole year, and they pay that each month. And it's terrible, and it's a subscription base, and the data now lives on the cloud, which pretty much violates a lot of laws. So it was just a terrible substitution. So the problem was that a lot of people say that software is more social than technical. So if that's the case, when you develop software, you have to deal with stuff that are inherent in human nature. And as we all know, our users are usually, most of the time, don't behave in a rational way. They make technical decisions based on design, on appearance, and on ease of use. And this is why Apple and Microsoft are multimillionaires, and Linux companies are still struggling. So if you're developers, I'm pretty sure you have had 1 or 2 contracts where someone is willing to pay you just to increase the size of a font or change an icon. Tell me I'm wrong. So that means that 95% of the users, end users of our products, are going to be people who are interested in looks, ease of use, and being able to understand the product quickly. They don't want to know anything about the stack, anything about the work we had to do to get the product done. So that means that we have to change the way we work to fit the 95% of our users. Because at the end of the day, if you're doing this as a business, you're going to have to let go of your technical preferences and do whatever helps you get your product out the door faster. So you have to sometimes let go of the stuff you really like to do. And this was a special case for me. I had to let go the Django solution we already have. And we had to make a list of reasons why I was having to let go of Django, even though I liked it very much for web apps. And in the specific case for geospatial applications, what the feedback that I got was, it was very easy to get started with GeoDjango, but it was very hard to keep the project going, especially if you're using, for example, CentOS. With every upgrade, the geospatial libraries will completely break support for GDAL and GEOs. So that means that every time you do a security upgrade or a minor upgrade of CentOS or Red Hat, your geospatial application in Django is going to break. Django has a very nice ORM, which means we can separate concerns of the applications and database. But when you go with Django and you do geospatial, the only feasible backend to use is Postgres. MySQL has support, but it doesn't have, for example, support for distance queries. So that means even though you have an abstraction layer, you end up using Postgres. And then you have the overhead of the ORM, the serialization, and the API. So why not get rid of all that in the first place and just use the database directly? The Django ORM is customized, is designed for textual data. It's not designed for digital, for binary objects. So serializing to JSON is very slow. Django doesn't have a native API framework. It has Django REST framework, which is a third-party option. It's very good, but it's not a native, so you have to install that. And on top of that, there are no native GeoJSON serializers. So you have to rely on a further third-party serializer on top of Django REST framework. And when you realize it, your entire stack is dependent on stuff that is not commercial, which is not bad. But when you do products at this level, you need someone whom you can call upon any time of the day or have a support contract, for example. So at the end of the day, it turns out that there was a very hard truth. Even though I love Django, it was not a good platform for geospatial applications, and it didn't sit very well with the Django community. But and even though I had a lot to say, and they had a lot to say, I said, but it's the hard truth. Django has a lot of really good stuff, but when it comes to geospatial applications, they are as useful as a sweater in the Mexican desert. So no matter how much you like it, you have to let it go. So now that we know what we can use and why, what's our delivery environment? And it's just lightweight spatial application that will retrieve data and just display a map. We're not trying to build, for the most cases, analysis systems. That means we're only trying to display a map about something else. For example, Airbnb is going to put a point of the property you're looking at. Uber is just going to track a position. Instead, sometimes we try to do entire platform to do geospatial analysis, to do reconversion of projections. And I learned the hard way that that's not the 95% use cases of geospatial applications. So what I did was I concentrated on putting them as much slowness of the process in the loading process, just like DNS does, for example. Writes are very heavy. That way, I can move a lot of the transformation and fetching of data into the loading process, and the retrieval will be as light as possible. That way, my maps will update almost instantly. So with our delivery destination clear, what are our guidelines for the next project? One of the things Libre was guilty of, it actually reinvented a lot of the stuff that existed. And sometimes we want to prove to ourselves, mostly more than others, that we can do something, even though there's something for it already in the free software ecosystem. So let's try to be more proactive in sponsoring what others have done and build upon what others have done, and not try to reinvent the wheel in every project. Another thing was that I learned the hard way is that no matter how good your project is, if it is hard to install, your clients are going to have a hard problem using it, and it's going to be an obstacle for adoption. So I learned to use Docker, not just as an infrastructure for scaling up. You can actually use Docker as a packaging solution, making your software being as easily to install as possible. Most geospatial applications will store geometries in binary format, which are completely proprietary internally of each database. I learned the hard way that there's something called GeoJSON, which is a serialized form for geospatial applications. And there's an even harder one, a more complex one called Car2DB, which actually stores the geometry and the projections. But for most part, even Car2DB is not even necessary for our applications. So serialize in the most simple format you can. It will pay a lot down the road. Geospatial applications can show a lot of things. It's not just points. They can plot lines, polygons with holes, intersect polygons. In the past, calculation of geometries was a very expensive process. So most geospatial applications tend to just use points. Nowadays, we know that points provide too little information. If I'm going to plot a route, I don't want points, I want lines. But with the computer power nowadays, it doesn't make sense to use points. So from the beginning, just go with geometries. At the end, your application will be much more expandable with practically no expense in performance. When you deliver your applications, you have a lot of options in the front end. And this seems to be like a religious topic with a new religion being born every week. I'm talking about JavaScript frameworks. So I'm going to get a lot of hate for this one, but I always stick to jQuery. I don't use React. I don't use Ansible. They're good, but the amount of overhead they include in the process, in the business sense, doesn't make sense. In the terms of design, a lot of people love to hate Bootstrap for whatever reason. From the business sense, I love Bootstrap, because I have these gigantic options of themes and templates that I can buy or pick, or It's a very knowledgeable framework. Everybody knows Bootstrap. So go with what is easier to get started. And the company ArcGIS has developed a very nice templating system called Calcite Maps that allows you to make mapping applications very, very easily, at least from the design point of view. And they even have an interactive style designer. Now, when it comes to data, we tend to forget that our applications are going to be running through the internet. And we get used to running them in a local environment where the data transmission is very fast. Some browsers like Opera have a very nice feature that can allow you to insert artificial latencies and bandwidth restrictions. Use that because most of the times our applications are going to be used by people who have very poor access to the internet. Even though our application might be lightweight, the data transmission between the front end and the back end could be gigantic. And like I said, also, don't do too much complex processing on the front end. Even though most browsers are able to run an entire stack, even when you include a React, a compiler, a transpiler, a CSS compressor, you end up with a lot of overhead, a lot of dead code that is being fetched back and forward or even included or linked that is not going to be used. And that stems from the idea that the browser is a computational environment. And it's not, it's just a viewer. So we have to make our front end as code lightweight as possible. And that's something I've learned the hard way. Ansible is great for doing data abstraction, but the amount of refreshes it does per second, something like 500 refreshes per second using a WebSocket, works great in my computer, which is a dual or 4th core computer. When you put that in a telephone, it completely freezes up. So even though you might hate me for saying it, just stick to jQuery. I have had 3-year-old projects which can be updated in 5 minutes because they are made in jQuery and I can re-deliver them. So usually I strike back from that one when people say it's just an ordinary and old framework. Another thing is trying to show too much information in the interface and our users get scared. And for geospatial applications, we have something called clustering. When you have too much information to use, you can actually group your geometries and show a simple detail or a summary of whatever is there. And as our users zoom in, you can show more and more details. So to not scare your users, use clustering. It's a very nice technique. It's a very inexpensive technique. And you can add it even after you have finished doing your map work because it's basically just another layer on top of your geometries. And I keep repeating this because this is the core of the talk. Don't over-engineer because you're making an app, not a platform. Unless you're trying to build a platform, then build a platform. But if you're trying to build an app, just build an app. Don't try to include data analysis, machine learning. If it is just a map, just make a map. ETL, okay. This tends to be considered a dead topic because this was very used in data warehousing, which is now another branch of data sciences. But for geospatial applications, it's very useful because that means that using scripting language like Python, which provides a lot of libraries for data processing, which was the birth environment of Python, Ruby, and Perl, are data processing scripting languages meant to glue together stuff and process data in batches. Is a natural environment to do deep processing of the data. And we have libraries like PETL, which provide a very nice environment to process data with iterators. And for everything that Django doesn't provide for geospatial applications, another name came constantly up for everything that Django didn't do. Another thing did, which was ElasticSearch, which was a big surprise for us because it is a search database. But they have geospatial querying application of support. It's limited, but because it is a search engine, a full-text search engine, it works incredibly fast. It's absurdly fast how fast it can deliver results. And it's a very tested, it's a very mature environment because it is already based on Lucene, which is an Apache search database. And it's already distributed and multi-tenant, so it can grow with as your data needs grow automatically. And for displaying the map, just go with Leaflet. It's very well understood, it's very mature, and it's been around for a long, and the main developer is also the developers of other commercial geospatial companies, so it's very well supported too from the commercial part. So at the end, this is our main map then. We have three main components. We have the data loader, which will convert our legacy data structures using Python transformations. It's going to store it in ElasticSearch using simple GeoJSON serialization. And then we are going to serve it with just a web server, which is going to serve a simple call site, a jQuery application, and it's going to query the Elasticsearch, and then it's going to plot everything using Leaflet. So we try to make the stack as simple as possible, reusing whatever it is that is available. To store the data, we create two fields. One is the one that's going to hold the geometry in JSON format, and what is the one? The other is the one that we are going to use to query, to index that data. And it's pretty much the same data. It's just that it has an idiosyncrasy of Elasticsearch. It doesn't allow to use a search field as a data field. So to store the geometry, we just use the nested file type, which allows us to put a dictionary, a Python dictionary, as a field. As a coordinate, for the coordinates, we do pretty much the same, but instead of adding the word geometry, the main key, we remove it, but we can store exactly the same data. There's a little bit of duplication, but this is a natural phenomenon in full text databases. There's a lot of duplicity, and they internally deal very nice with that. And Elasticsearch has natural support for geo-shaped data types, and they're automatically indexed, which is something very hard to do in Django. And good indexing means no matter how much data you add, the search speed is not going to get affected. And it has support for all the basic geometries, point, lines, multi-lines, polygons, multi-polygons, multi-lines, and even geometry collections, which is a geometry that's a point, a line, and a polygon included in just one geometry. And this is a typical query that you do with Elasticsearch, because Elasticsearch is naturally REST-based. You don't have to install a separate client. You don't have to code anything. It's natural language. So to query the database for a specific location, you create a runtime geospatial primitive called circle. You give the coordinates and you give the radius, and it will give you everything that's inside that radius. And it will return you something like this. It will give you the time it took, all the results out of this many. I will tell you, I'm giving you this because it's coordinated were this, and they were inside what you asked me. And this is the complete geometry you asked me. This is what we are going to use to plot something on the map, which in this case is a point with these coordinates. And these are its properties. And these are just application properties. And it's just a dictionary that we're going to use, for example, for the pop-up, for the details when the user click on that. On the Python side, to load all this, we just need to create a simple class for each dataset that will encapsulate the ETL engine. And we just expose the simple method that PTEL exposes, which is to grab something from somewhere, make sure it's cached, we transform it, and we just upload it into Elasticsearch. And this is the example for the dataset of the public transformation shapefile, which is, it's actually not a shapefile, it's a comma delimited text file that has geospatial information. It's a nightmare to work with. But with PTEL, we can transform that very easily. When we load it up in Python, it's all this mess. And when I load it up in LibreOffice, it showed me that it's actually an Excel file. So with PETL, we can do string manipulation very easily which doesn't show in the with the projector very nicely. But what we can do is transform all this text mess, do a lot of what Python does very nicely, which is string manipulation, and at the end we can convert it into a dictionary that's GeoJSON compatible. And that's the magic of the T in the ETL process. We can change whatever the file format we're given, which in case of the governments is usually very bad in quality. And I'm not just saying that just to sound funny, it is the truth. So much that even when we were given the crime data sets, even the coordinates were inverted. They didn't know even what a latitude and a longitude was. The dates were completely wrong too. So what we do is we subclass our dataset class, one for each dataset, and then we can customize the transformation method for each dataset. So when we deal with geospatial files, the Python ecosystem has 3 very nice libraries. I recommend you, if you have to deal with shape files, become very accustomed to these 3 libraries. They're going to help you a lot. You have Fiona, which is perfect at understanding a lot of strange and commercial shapefile formats. You have PyProjection, which is able to transform the projection of a lot of geospatial files. And what are projections? Projections is just a way to represent something that's round into a flat plane. And there's a lot of ways to do that. But with computers, now we are able to project coordinates in real time using one single projection, which is a GeoCO projection, which is what Google Maps uses. So this is basically being phased out. And you have Shapely. Shapely can transform geometries. For example, you can do simplification of geometries. You can do mathematicals to make sure 2 geometries are intersecting. And if they are intersecting in your specific case used, you can remove them. So that analysis, when you're transforming a shapefile to see what you can discard or you want to keep, you can do with Shapely. It is very good at knowing if things touches, intersect, or are being included in. So it's basically algebra for geospatial objects. So yes, GIS sometimes looks kind of unwieldy, but once you get used to it, it makes very much sense. It's just trying to represent the world in a flat plane. So with those 3 libraries, we just open it with Fiona, we transform it using PyProject, and then we change our geometry into GeoJSON using Shapely. For the front end, we use CalSiteMap, which, as I mentioned, has an interactive style editor. And after using it, we came up with this theming, which was very, our kind looked at very much. When we add a simple toolbar for selection and localization and changing the layers, and a detailed plane. On the JavaScript side, since Elasticsearch is already REST aware, we just build a simple wrapper, which is just wrapping geoqueries getJSON call. And for each data set, we build a counterpart class, or in this case, a prototype for each data set that will just hold a simple metadata of each data set. For example, the template of what is going to appear when our users click on a point, or the icon that's going to be displayed for a specific feature. And for each item, we just clear the layer and we just re-add. And when the layer has completely has finished loading, we launch our callback to calculate whatever is going to be displayed in the information pane of that layer. It could be a summary of crimes. It could be a summary of crimes per year. And this is very much the callback for the construction permits layer. It's just gonna show a ordered list of construction projects. It can be very simple, it can be very complex. And at the end, this is what we end up with. So to select a specific area, we use a Leaflet plugin called Leaflet Draw that allows people to draw shapes. We restrict it for just circles. We add a simple, we customize it to show the geometry of what the user is selecting. and we capture the event of the draw create. Then we construct a Elasticsearch query using a circle geometry, and you will just send that, and whatever we get, we pipe back into the geospatial prototype for each data set. And we end up with a complete system that can show information about public routes, crimes, construction permits, schools, economy living standards for every specific part. We are, in this project specifically, we are merging 7 different data sets in a single map. And we can have information pop up for a specific location. And when you pop on it, you have an information pane. I'm going to publish this because the resolution of the projector is not helping. And you can change that into for using, for example, aerial photography, and you can pinpoint exactly when the point lands and see what's the crime rate at a specific area and decide whether you want to move there or not, which is the purpose of this project for the government. Now that our 3 amigos are finally singing together, what do? We have to deliver them. So we have to put them in a single container or in a single package. So for that, we use Docker. And since we're reusing everything that's available, every single thing we are using for our project has an official Docker container. So what we do is we create a Docker file and we build upon the official Docker file. This is the one for Nginx. There's Nginx that's going to be serving the front end. This is the one for the manager that's going to be doing the transformation. And this is the one for Elasticsearch. As you can see, the Docker files for each part of the project are very small because we're just customizing a little bit what's officially out there. For Elasticsearch, we add a single plugin that's going to restrict writes to just the local network, so to disallow internet users from changing the data because we're exposing a port. And what it does is allows only GET requests that are not contained from the internal network where the project is running. With that, we basically secure it very much. And we can add also a automatically generated password between Elasticsearch and the transformation engine, just in case. So we're almost done. So to deploy it, since we are using Docker for packaging, we can just create a Docker compose file that will launch all the 3 different container images, and that's pretty much it. We just run Docker compose up. We copy whatever data it is not being fetched automatically because these are managed by hand. These are 2 geospatial files. Then we run the manager, which is the transformation engine. It will transform the data. It will store it in Elasticsearch, and then our map is ready. So it is very easy to deploy, to develop, to update, to run, to teach to our users. And don't tell me you haven't done that when a project really goes out in time. So we have time for a little bit of a demo, or just, okay. Okay, my map doesn't want to work because I'm offline. I forgot about that part. So no demo then. But this is an official government project. I'm going to publish the official URL when the government of Puerto Rico publishes this next week. This is still an unpublished work, so you're getting a very timely preview of what is going to be available in the government of Puerto Rico with pretty much no budget. So I don't know if you know the fiscal situation of Puerto Rico, where it is actually being stripped by 4 parts and being sold to pay the debt. So government agencies has had their budget cut by more than half. The university actually lost $400 million in budget, the official state university. So projects like this are gonna keep ideas, method of developing applications, helping us keep the government up to date in technology. So I know I said a lot of bad things about Django. So if you're mad with me, here's a photo of badass Mexican actor Danny Trejo, alias Machete. I recommend you see his pictures uh, for uh, for your soothing. Thank you very much.
Hi, thank you very much for this talk. There is a lot inside and a lot of tools. And the question is about the tools. If you can just summary, just few words of, well, first of all, why you are using Elasticsearch instead of, for example, MongoDB, and why Postgres. And you said that it's important to use a tool with a commercial background. So why you are using, for example, Leaflet instead of OpenLayer, that is maybe a library that is more inside the commercial point of view. And you said monolithic problem. I think that jQuery is monolithic, and all the frameworks that actually came up was they wanted to resolve this problem. And for example, React is just a library; it's not monolithic.
Well, the question is very layered, so I'm going to try to remember. The cost and time of the project is not just the development, it's the tool selection process too. So a lot of that was I found out about this library first, and I understood it fast, so I stopped looking at other stuff. Now, I didn't know anything about open layers, you mentioned. I have no idea about that until now. So I'm definitely going to research that. So if it proves faster for me to learn it on our team and faster than Leaflet, we're going to definitely choose it because it's going to make more sense to the bottom line of doing it fast and delivering it fast and being cost efficient. So a lot of the reasons was that I haven't found out about the ones you talk about. React, I tried to use React. We tried to use React. We had a hard time understanding it. So it's not that it's bad. It's that in that case, we chose like the Python PEP 8. You try this, simplicity matters unless it makes things more complicated. So for us, even though it was a step back in terms of modularity, it was much more easy to understand. So it was just a matter of time, not a matter of quality. Thank you.
We have time for one question. Okay, question. Thank you.
Thank you very much.